Hello students, welcome back. Let's go to section 4, non-homogeneous linear ODEs. Here is a general structure, L of y equals to f of t. Now, if the right-hand side is constantly 0, then this is a homogeneous linear ODE, which we studied in the previous section. In this case, we have f of t, which is not always equal to 0, so this is non-homogeneous. In any case, our aim is to find a general solution. But then again, there's another term with solution in it, and that's creating some confusion. What's the difference? Now, this distinction is extremely important. Once you get it, then this entire section will not give you too much trouble. If you don't, then you'll struggle here. So let's take care of it right here, right now. All right, ready? The general solution is not a solution. It's a family of solutions. It's a family of infinite many solutions, and it comes with the undetermined parameters, C1, C2, C3, those kind of things. And therefore, it works well with the initial condition. Put everything into the initial condition, put all those numbers in, and you're going to get a system of equations with all these undetermined parameters. Now, if you begin with a linear ODE, then you're going to get a system of linear equations of these undetermined parameters. So you can solve it and you're going to get a unique solution. And that unique solution of undetermined parameters will give you the unique solution of the ODE and the IC, the one and only solution that you want. Now, if you start with a nonlinear equation, however, you're going to get some possibly messy systems of equations which may or may not work very well. And also, in the end, you're going to get possibly some singular solutions or non-unique solutions or no solutions, or some messy intervals of definitions, whatnot. But then again, our focus here is linear ODEs for the time being, so let's not worry too much about nonlinear case. In any case, linear or nonlinear, our aim is to find a general solution, because everything that we can do is coming from the general solution. Now, the particular solution, that's different. It's just one solution. It's not one solution, one function, so there's nothing undetermined. If there were any one undetermined coefficients, then change this value, then you're going to get more than one functions. That's not the case. A particular solution is just one function, so there's nothing undetermined. Therefore, it does not work with the initial condition. It has nothing to do with the initial condition, and that's really important. If you plug that into an initial condition, all you're going to get is pass or fail. You cannot work it out and solve anything because there is nothing to solve for. There's nothing undetermined here. So, if you have an equation, an IC, and if you want a solution, then the chance is this YP, the particular solution, is not the one you're looking for. Unless by a sheer luck, you get this. But of course, that kind of probability is zero, mathematically zero. That never happens. Then, how do you use this YP? Right here. YP, the particular solution, this YP may not be the solution you want, but it helps you finding the solution you want. What you want is a general solution, this left-hand side, y of t. It turns out that y of t is equal to yh plus yp. Yp is the particular solution, a solution of this ODE, even though it may have nothing to do with the initial condition that we have or you will have later. Now, how about YH? That's a general solution of the homogeneous equation, Ly equals to 0, something we studied earlier in the previous section. Now, brush up your memory from the previous section. What does this YH look like? It looks like this. In case of second order, this is a structure. Now, if you have general terms like this, then you're going to get arbitrary n. So this is a linear combination of n linearly independent solutions of the homogeneous equation Ly equals to 0. That's the general solution. Now, if I put this into this expression, what do I get? This is what I'm going to get. Y of t is equal to, let's put this expression in, and plus yp. Let's highlight this one in red, and the other is blue. So YH part has all the undetermined coefficients, C1, C2, C3, and so on. YP, on the other hand, this one has nothing undetermined. So in the end, we have a solution with a lot of undetermined coefficients to be determined. So this will work as a general solution. Let's check. Let's check. What if I apply this L? Then by the linearity property, it'll apply here. Oops. Let's copy and paste correctly. Okay, it'll apply here, and then it'll apply there. And then in the end, what do you get? This one here is L of the solution of the homogeneous equation. This one, so it has to be 0. How about L of yp, this part? Yp is a solution of this original. It's a solution. It may not have anything to do with your initial condition, but nonetheless, it satisfies this. So this is f of t. So what did you get? This expression is indeed a solution. This is precisely what we wanted. L of y equals f of t. Yes, 0 plus f of t, so it works out. And then also, it has a lot of undetermined coefficients, C1, C2, and so on and so forth. And therefore, it'll work well with the initial condition, if any. So that's a verification. Now, if you want to prove everything precisely, then the proof is here. But don't be fooled by this briefness of the proof. It may look like just 2 lines, but it has 2 non-trivial ideas, so it's actually a bit tricky. We are going to discuss it in the next chapter of our textbook, chapter 4, or in terms of my notebook, lesson 7. At this moment, let's just focus upon how to use this, YH plus YP. YH is something we already discussed, so how to find YP is the focus of the section 4. Okay? All right. This distinction, YH versus YP, or Y versus YP, that's the focus. If you understand this conceptually, then nothing else will give you too much trouble here. All right? Our focus is what? How to find YP. How do we do that, actually? Before going over to an example problem, let me give you a brief overview on the on this topic, 4.3, finding particular solutions. If you use the Laplace transform, it goes like this. The Laplace transform of left-hand side and right-hand side. And the right-hand side, f becomes capital F, all right? In the left-hand side, by the input derivative rules, we have all these and take the like terms together. We have done this before in chapter 2. What do you get? You have q of s, a characteristic polynomial times y, and then a polynomial of degree at most n minus 1. Let us name them as q of s and r of s, like this over here. And then flip over r of s and divide by q. What do you get? We have r over q, the homogeneous part, and f over q, capital F over q, the particular part. You see, we are looking for what? We are looking for yp. And there you go, capital YP, the Laplace transform of it. So if you take the Laplace inversion, you're going to get that small yp. That's one method. Next method, substitution method, which I'll talk about later after completing one problem. Here we go. I think we'll have time for only one problem, so here we go. Let's do the first problem, the easiest one. Now, do you recognize this problem? I'm in the left-hand side. You've seen it here, right here. So the homogeneous part is something you already did, so you can recycle that result. All right, let's go to method 1, the Laplace transform method. The homogeneous part, this is something we had been doing in chapter 2 time and time again. Capital Y of H is, capital YH of S is R over Q, and factor Q, the denominator, and decompose it by partial fraction. This is what we get. And then what if you take the Laplace inversion? This is what we get, C1 over 3 and exponential of 2/3 t, oops, okay, and then C2 over 2 exponential of negative 5/2 t. Did I do this right? Okay, let's include this one in. By the way, we have this 3 and 2 in the denominator because of these coefficients there, but then again, why would anybody bother with these messy denominators here and there? Because all we have to do is to find a solution, so you can put something arbitrary here and there, rather than C1 over 3 and C2 over 2. As a matter of fact, that's what I did in the end. I replaced those into another character, K1 and K2. Sometimes I just leave the same character C1 and C2, even though they're not exactly the same. Now, how about the non-homogeneous part? That's the key, right? That's the main aim of this entire section, the non-homogeneous part. As you saw before, this is capital F over Q. So how do you find capital F? We start from the right-hand side, f of t is 5t, and take the Laplace transform. Look up the table in page 123 of our textbook. We have t, and then that's going to be 1 factorial over s to the second power. And of course, we have multiplied by 5, so we have 5 over s squared. Put it into the numerator here, and simplify a little bit. And then focus upon this factor s squared when you take the decomposition by partial fraction. This is an extremely messy computation, but of course, I didn't do it by paper and pencil method. I used Mathematica for that. Focus upon these two, which are highlighted in red, because the others will be absorbed by the homogeneous part here. You see, we have the same thing, 2s plus 5, 3s minus 2, both of them appear here. So take the Laplace inversion of this part only, and then what do we get? We get this. Previously we got that, so add those two together, then we get the solution. That's a Laplace transform method. As a matter of fact, we had been doing this from chapter 2, as a matter of fact. If I remember correctly, we did this very same problem in chapter 2. If I'm wrong, well, maybe I'm wrong, but even if I'm wrong, I'm pretty certain that we must have done similar problem with some different numbers. Now let's go to the second method, the substitution method. The homogeneous part, and you can just substitute e to the st in there and then try to work those out, but in the end you get the characteristic equation, and then we get the eigenvalues 2/3 and -5/2, and then you get the linearly independent solution, e to the 2/3 t and then e to the -5/2 t, and then you take the linear combination of those. That is the general solution of the homogeneous equation. We did it in section 3, so let's move on. How about the non-homogeneous parts? Let's begin with an educated guess here. AT plus B. Why did I do that? That's because this non-homogeneous part, f of t, is a linear polynomial. If this is a polynomial of order k, then you put a polynomial of degree k here. I'll talk about the detail after this problem. For now, let's go from here. Let's take this educated guess and take the derivative and the second derivative. Put those into this original ODE. And let's work those out, and then let's find a and b. Ready? Second derivative goes to this y double prime, so this entire second derivative term just drops out, so that's 0. First derivative goes over here, so we have a. And the original function, at plus b, goes over here, and we get this. And in the end, we get the following form. Now, take the like terms together and compare the coefficients. The t coefficient is 5, and that is equal to -10a. That gives me the first equation. And then the other gives you the second equation. We have a system of linear equations. 2 unknowns and 2 linear equations. We can have unique solution here. And yes, indeed, a is -1/2, b is -11/20, and we have the particular solution. Add them together, then you get the solution, and of course, we have the same thing as the one you saw before in solution 1. Now, which method do you prefer? The key portion is to find the non-homogeneous solutions, so let's compare these two. The Laplace transform method, capital F over Q, and taking the decomposition by partial fraction. Or start with an educated guess, put those into the original equation, take the like terms together, and get a system of linear equations to solve. Which method do you prefer? Personally, my preference is the first method, if, big if I'm allowed to use the computer algebra system. If I don't have Mathematica, then I'll probably have to set up a system of, oh my goodness, probably 4 unknowns and 4 equations and getting it done. I don't like this. I'm not going to do that. I'd much rather do it this way. So with computer, I prefer to do it this way. Without the computer, I'd prefer to do it this way. It's not a coincidence, by the way. The theory of linear ODEs were developed in, if I remember correctly, in 18th century. And of course, at the time, there was no computer, and people developed this kind of method. This one is relatively new. Still, Laplace was a mathematician who lived in 19th century, so still, at the time, there was no computer, but still, it's relatively newer. Anyway, let's go back to this educated guess, because everything hinged upon this one. Let's go to this 4.3, and let's open this. And here's a table. And I forgot the page number from our textbook, but I'll post it in Canvas. It's taken from our textbook. So if the right-hand side, the non-homogeneous part is like this, then we start with this kind of educated guess. The special case, if we have a polynomial of degree k, then we begin with a polynomial of degree k. That's what we did in the previous problem. And of course, we have to consider other cases as well, and we're going to do those in other problems. There are 2 more exercise problems here, and we're going to talk about those in separate videos. For now, let's stop here.